Let's wait for 2-3 minutes. After that, I will start. Okay, let's start. So this is week 10 problem solving sessions. So today we will be discussing mostly first the assignment questions, of course, assignment questions of week 9, and then we will go for the week 10 content, that is on the dummy variables, right? And the third one is that we will do one practice question based on the week 10, that is the dummy variable concept. So this is our plan today. So first is the assignment questions for week 9. So we will be doing that. Okay. So I just okay. So let's start with the assignment question, week 9. All right. So let's see the assignment 9. All right. So the first question is, suppose that we want to fit the no intercept model, that is y is equal to beta x plus epsilon, using weighted least squares. Assume that the observations are uncorrelated but have unequal variances, and it is given that let the weights wi is 1 upon the variance of y. So a general formula for the weighted least squares estimator of beta is what? Based on all the options are there. So we have to find out what is the unbiased estimator of beta. That is what required. Okay. So based on our previous concepts, which we have what we have discussed in the last problem solving sessions, that whenever you are being provided with the weights of which is dependent on, it is inversely proportional to the variance of yi, there you have to use the weighted least square technique, and we have discussed the last entire session the weighted least square technique. So it is based on that because it is already given, right? So to solve the first question, we will first write that what is the model. So it is just beta x plus epsilon if you write. So it's a no intercept model. No intercept model, and here only one regression is given x. Okay. So what will be the fitted model? That will be y hat is equal to beta hat x. No epsilon will be there. Right? So this is the fitted model. Right? So this is the fitted model. Now weights are being already given. That is 1 upon v of yi. That is, this is the variance. Okay, variance. So wi is already given. Now, simple ways to solve this, we will use the same concept which we have used in the simple linear regression model while we are estimating the beta hat. Right? In the same way, we will be using. So we will be starting with the S, which is the residual square, that is EI square, the sum of the residual square. So what is that? It is yi minus yi hat whole square, because it is sum of square of residual. I is equal to 1 to n. Let us say that there are n observations because it's a generalized way. So S, we can further write. I'm not writing the I again. So it will be just yi minus the fitted one. That is y hat. So it will be beta hat x hat whole square. So this is your S. And the entire thing in the regression analysis is to minimize this S, the sum of square of residual. So what we will do for the minimizing the thing, so we get delta S by delta beta hat, and we will put it 0 to get the beta hat. But in case of weighted least squares, we cannot do this. We have to multiply this with the weights. That is why it is weighted least square. So this is the weighted. Okay, weighted least square technique. So here also you have to multiply with W. Now this S, it has to be differentiated with respect to beta hat and put it equal to 0 to get the minima condition. Okay, to satisfy the minima condition. And if you do it, then you can clearly see that it will be, the summation will be remaining here 2 times yi minus beta hat xi, and you are differentiating with respect to beta hat, so it will be minus xi, right? So this times wi, the wi will be always there, so that will be equal to 0 because this is the condition. So we have done that. So 2 can be removed, so because it's a constant kind of a quantity, we cannot, so we can easily remove it. Other terms are exact wi yi, because these terms w, x, and y, they consist of this I, and the summation is in I. So therefore, we cannot chop these things out. Okay, so this will be there minus, and this you can see that. Okay, this minus can be taken outside. That is also fine. So it will be beta hat xi wi xi square. Sorry, this xi is there. So this will be equal to 0. Fine. So finally, what we are getting is that, so it will be summation xi yi wi will be equal to beta hat xi square and wi. Right? So what we require is beta hat. Beta hat being a constant can be taken out of the summation. So you can just write xi yi wi. Beta hat can be taken out. So it will be xi square wi. So finally, what will be beta hat? So it will be summation xi yi wi divided by summation xi square wi. So this is your beta hat, the unbiased estimator for the weighted least square because the weights are given here, right? So this is your final solution. So if you, so it will be summation xi yi wi divided by summation xi square wi. So let's see what is the solution here. So you can see that the accepted answer is that beta hat is equal to summation xi yi wi divided by summation wi xi square. So this is the answer which we have got. Okay. Now in the same question, suppose it is given that the variance of yi is pxi. That is, the variance of y is proportional to the x. Okay. Using the result of the problem 1, the weighted least square estimator of beta will be 1. And there are so many options. So let's see. Okay. So what changes we need to do? We know, okay, so for the second question, we have to use the same this beta hat. So let me write it again. So beta hat is xi yi wi in the numerator divided by summation xi square into wi. So this estimator we will be using, but it has been given that, so it is given that v of yi is c times xi. So variance of y is proportional to x. Okay, this is given. Now we also know from problem 1, we also know that wi is nothing but 1 upon v of yi. It is given in the first problem. So that will be 1 upon c x I. Remember, this is the constant. This is given in the question. So just put it, therefore, beta hat will be then what? Xi, yi, and this will be 1 upon c into xi. Right? Divided by summation xi square, and this will be 1 upon c x. Right? So just now within the summation, you can of course cut this xi which are present. So this xi can be removed. This xi and this xi is removed. So what finally you will get is that in the numerator you are getting yi by c divided by, in the numerator you are getting xi by c. So see now this c is the constant. It does not depend on the summation. So 1 by c can be taken outside and can be chopped from the numerator and denominator. So finally we will be getting summation yi divided by summation x. That's all. This should be the beta hat if your variance of yi is xi. It's proportional to x. Okay, so this is the answer. So if you go to the second question, you will find that beta hat will be summation yi divided by summation xi. Fine. Let's go to the third question. Suppose that we want to fit a no intercept model just like the previous one using weighted least square. Given. Assume that observations are independent, but now variance of yi is k times xi square. Okay, is proportional to the square of the corresponding. The least square estimate of beta then will be what? Okay, so let's try this. So this is the third one, right? We will be using the same thing. Okay, because ultimately for the weighted least square technique, and if it's a no intercept model, then this will be used, right? Because we have derived it from that condition. So it is already given that it has to be a weighted least square. Number two is that it is given that it's a no intercept model, so it is beta x plus epsilon, no intercept. Okay, and and it is also given that variance of yi is actually kxi square, right? It's the square of the xi. So based on the first two, we can use beta hat is equal to what we have got from the first question, because that is also a no intercept model and we have used a weighted least square technique. So we can use this. Okay, so this will be xi square into w. That's all. Okay, now in the wi, we have to use the different variance because wi, as we have seen, is 1 upon variance of yi, right? So here we have to use that. Okay, just in the formulation, you have to just put the wi. Okay, so this is xi, yi. What is wi? 1 upon variance of yi. So what is that? Kxi square, right? This is your wi. So let me just quickly write it. This is xi square divided by summation xi square into wi. So what is that? 1 upon k xi square, right? So you can clearly see in the denominator this xi square, it can be chopped up. This and this will give you one xi. Okay. So finally, if I write, this becomes summation yi divided by kxi. Okay, this is in the summation divided by summation 1 upon k. Right? This is what we are getting. Well, then what? In the numerator, this 1 by k can be taken out of the summation because k is a constant. Okay, so this will be therefore yi by xi. Fine. But in the numerator, so in the denominator, this summation is on 1 by k. So n times, if suppose I is equal to 1 to n, there are n observations. This 1 by k is added n times. Then what will happen? It will be n by k, right? Because this 1 by k is summed over from I is equal to 1 to n. So n times it will be repeated, same constant. So it will be n by k, right? So this k, now this k can be removed. So it will be just 1 by n summation yi divided by xi. Okay, this is in out. The summation is in out. So this is your beta hat when you have been given that the variance of yi is proportional to the square of the corresponding x. Okay, so let's see. Let's check. Third question. See, this is 1 by n, yi by xi. In the summation, it is yi by. Okay, so we are getting what is there in the option. Okay, fourth is consider the same problem. 3. Expected value of beta is. Well, fine. So in the fourth question, you have been asked to find the expected value of beta, or you can say that beta hat. Okay, the unbiased estimator, what is the expected value of that? Right? Because when you are calculating the so yeah, so this is what you have to do. Correct? So E of beta hat is nothing but expectation value of whatever we have got, because it has said that in problem 3. So problem 3 is this. So 1 by n summation yi by xi. That's all. This is what you have. Fine. Now, what you will do is that 1 by n doesn't matter. It will come out summation expectation value of yi simply. Xi will not matter because xi is an independent variable. It's not a random variable. We have started this discussion long ago from the week one only. We are saying that this xi is an independent variable, so it does not matter. All right. So we will be using this to understand. Okay. So this will be 1 by n as it is. And further, what we will do is that just let me start with this now. Yn is equal to beta xi plus epsilon I. This is given as the no intercept line, fit, not fit, but the model. Now, if I take expectation value of yi, this will be what? So you have expectation value of beta into xi plus expectation value of epsilon I. But according to our assumption, that expectation value of epsilon I should be 0. Why? Because epsilon I is assumed to be normal 0, comma sigma square. Right? So this is 0. Expectation value of epsilon I is 0. So we can remove it. Therefore, E of yi divided by xi can be written as E of beta, which is nothing but beta only. Right? Because beta is nothing but a constant quantity. So it will be beta. Correct? So if I now come here in this part, so what we are getting E of beta hat is nothing but 1 by n summation of E of yi divided by xi, which is nothing but 1 by n summation of beta. Right? Because this is what is inside, and this summation is n times beta, so it will be n beta divided by n, so it will go, so it will be only beta. Therefore, expectation value of this beta hat comes out to be equal to beta. That's what is the question. Okay, so if you come to the question again, so you will find that, not this one, yeah. Consider the problem here, the expected value, it should not be beta, I think it will be beta hat. So the beta hat expectation value is actually beta, the first one, this one. Okay. Now, the fifth question, consider again problem 3, the variance of beta hat. We have seen the expectation value. Now we will be seeing the variance of beta hat. So this is the problem 5. We need to see the variance of beta hat. Okay. Fine. So we'll start with the same thing. Okay. So beta hat, we know that from problem 3, we have got 1 by n. This is summation yi by xi. This we have got already. Now, variance of beta hat then will be what? So again, just remember one thing. Whenever you do some variance of c times y, where y is some random variable and c is some constant, then what you do? You write this as c square. The constant will be squared and variance of y. This is what you write. Same thing you will be applying here. Okay. So this 1 by n is a constant. So can I write this 1 by n square? Yes. Summation. Okay. So it will be variance of yi, no doubt. But this xi will also be a constant here because this xi is an independent variable. It is not a dependent variable. It is not a random variable. So this will also be squared. Just remember this. Okay. So therefore, v of beta hat will be 1 by n squared. So variance of yi, what is that? Variance of yi is a xi squared given in the question problem 3 and divided by xi squared. Let it be the summation be there. Does not matter. So now I can chop off this. You can see here it is n times summation of the same constant k. So how what it will be? The summation of k n times, it will be n times k. Correct? So this n and n will be chopped off, so it will be k by n. The variance of beta hat is k by n. Okay. So here it will be the second option, k by n. Now, sixth and seventh are easy questions. So in the sixth question, it is being asked that can the model y is equal to beta naught upon 1 plus beta 1 exponential of minus alpha x can be linearized or not? Let's see. So this is, I think, the sixth question. What is being asked? So y is equal to beta naught upon 1 plus beta 1 exponential, that is right, minus alpha. Okay, can it be linearized or not? This is the question. Okay, so let's see. Let us inverse y first because you can see that most of the terms in the summation are in the denominator. So the possible way is you to reciprocate y. Let's see. So if you reciprocate y, what you get? 1 plus beta 1 exponential minus alpha x divided by beta naught, right? So 1 by y is equal to, therefore, can I write this? 1 upon beta naught plus beta 1 by beta naught into exponential minus alpha. Okay, one step is solved. At least we have got separated two terms. Now, still the x and y are not completely separated. So, can we take log and remove the exponential? But thing is that if you, whenever you take log, suppose log of 1 by y, look at the right hand side. It has 1 by beta naught plus beta 1 by beta naught exponential of minus alpha x. Log of a plus b cannot be written as log a plus log b. So this cannot be done. Means at least we cannot linearize this. Therefore, we have to stop it here and we say that no, if you take log and to remove this exponential function to make it a linearized function, you cannot use log or any other means. So therefore, this model cannot be linearized. Okay, because if you take log to remove the exponential function here, which is present here, you have to use some way to separate out these two things. But log cannot separate these things. Log of a plus b cannot be written as log a plus log b. So that's why it cannot be linearized. Fine. Let's go to the next question. So its answer is no. Suppose you have n observations and there are so many variables. Suppose y's are exponential variables. We consider fitting of this model. What is the reasonable choice of fy? Okay, we know this. This is very simple. So the eighth question. So suppose y is this is suppose some exponential variable. Okay, some beta naught into exponential. Just see this beta one y. Suppose or x. Okay, some exponential function. Then what? How will you linearize this one? So simple thing is to take log y. That's all. So here you can take we see log beta naught some exponential function minus beta one x. We have seen this, right? So this can be written as now log beta naught plus log of this. So this, which will be minus beta one into x. So this is now a linearized function beta one x. Question is that what transformation you have to make in y? So that will be log of y. Log is the answer. Okay, log, natural log or whatever you want to say. So it will be log of y. Fine. And the last is also simple. Suppose we have seen this, we have made a table of this. Suppose you have n observation of variables, so many things. Y is the response variable and y is a Poisson variable. We consider fitting of the model. So simple that for the Poisson variable, you know that your suppose this is this is I think seventh. For the eighth question, it has been said that y is a Poisson. It's a Poisson function, and with some parameter, say lambda, you can take whatever you want. But in this case, in case of Poisson distribution, your variance is actually proportional to the expectation value of y. But exactly same. The variance or sorry, the standard deviation or say the variance. No, no, the variance and the expectation value they are same. That's why we can write that sigma square, the variance, is proportional to E of y. And when this kind of thing happens, we know that the transformation is f of y is equal to root y. We have seen this. Just you can check. I think the last to last week lectures. Okay, so this is the transformation which we need to use. Okay, so this completes the assignment, all assignment questions. The last answer is root y. Okay, so let us therefore move to the next part. That is, we will discuss the week 10 content, that is the contents of the dummy variables. And in between, we will solve one question that will give an idea of how to solve certain things. Okay. So now the week 10 content, which is on dummy variables. Just a minute. So what is the concept of the dummy variables? Is that there is a very famous problem which is being discussed in the video lectures. That is the Turkey data problem, which is being discussed properly. And I will be using some part to understand that. But what happens is that, let's say, there are you are an oceanographer. So you are an oceanographer. You are going into a vessel uh, in a through a ship, and you are observing certain things. Like for example, you are observing sea surface temperature, sea salinity. These things you are observing, and there are many other variables. Okay, so you are observing some relationship between the sea surface temperature and sea salinity. For suppose, okay, and you are uh, getting some data. Let's say this is some x1, x2, x3, and so on, and you are seeing that how y1, y2, y3. This means based on x1, how the sea salinity is varying. Okay, so your first location is suppose, let's say, Bay of Bengal. Okay, first location is the Bay of Bengal. Next is you have come at the south of the India. That is, you are now on the Indian Ocean, over the Indian Ocean, and you are taking some samples and try to see some relationships. Okay, so this is Y4, Y5, Y6. Okay, let's say this is over the Indian Ocean, the south part, near Sri Lanka and Indian Ocean. And after that, what is happening? You are going to the west of the India, where you have Arabian Sea. And in the Arabian Sea, you are also taking some observation, like three observations in the Arabian Sea. And corresponding salinity, you are also observing. Now, so this is suppose Arabian Sea. But now, if you are not a oceanographer, you are just taking the observations and let's say you want to fit a linear relationship between sea surface temperature and sea salinity. Suppose you are trying to say it might not be the linear relationship, some other relationship. But let us consider for the time being that you are trying to fit a linear relationship between sea surface temperature and sea salinity. Okay, so you know how to do that. You have one regressor variable SSP and one response variable sea salinity. And so you know how to make it. So beta hat you will find. So you just fit y is equal to beta x plus beta naught plus epsilon. Right? This model you know how to fit, and you have fitted based on all the observations you have fitted. But what happens is that you take this linear fit and go to one oceanographer and you are saying that this is what the relationship is. Then the oceanographer asks you that, okay, let us see what are the data and how you have done that, how you have fitted the model and all those things. But when the oceanographer sees it, he immediately picks up the point that you have done something problem. Some problem is there. Why there is some problem? Because you can see that first three data what you have are from one particular ocean. Second sets of the data are from another ocean. Whereas third set is Arabian Sea. That is another ocean. So these oceans, these relationships within each ocean basin may be different. Maybe. I'm saying that maybe. It may come to this linear fit of all this data. You can find out that the residual term, that is the EI, yi minus yi hat, may be somewhat higher in other cases. Like in Indian Ocean, it might be larger than the Bay of Bengal and something like that. So based on that, you can easily pick up the thing that there is some problem in the data. So immediately you understand that okay, Bay of Bengal behaves in a different way, Arabian Sea behaves in a different way, and Indian Ocean behaves in a different way. Therefore, we need to understand in a better way. Here comes the concept of the dummy variables. When you have different sets of data, that is some kind of a qualitative kind of a nature, a categorical kind of a nature, there you have to use these dummy variables. Okay. So this is one of the examples I wanted to give. So through that, it might be clear. So for what happens is now you can call that this is A sum, this is some B set, and this is some C set. Okay, and based on that, you have to create a linear regression model so that we also take care of the different sets of data. Like for the Bay of Bengal, we have one kind of a set of data. For Indian Ocean, some other, and for Arabian Sea, some other. Okay, so this is the concept of dummy variable which we will be talking today. Fine. So let me just first write and give the introduction of this. Okay, so suppose we want to introduce a model, okay, where the idea is that there are two sets of data. Here we have three sets of data. So there are two sets of data. Let us reduce it. Okay, two sets of data. Let's say A and B. Okay, sets of data. Okay, that produces different levels of response in addition to the variation that occur due to other regressions. Okay, so now, so you have two sets of data, just like what I have explained. Suppose you have Bay of Bengal and Arabian Sea. Let us say A and C. These are two sets of data, and you have some observations. When you are fitting it based on all the data, you will find out that the residual term, that is the EI, that is yi minus yi hat, the fitted response minus the observed response, you will find that there is a significant difference in them. That suggests that you cannot take it together. Sometimes you may get it together, may get a good relationship that represents that okay, you can take it together. But sometimes if you are not getting the good relationship, you are seeing that the residual terms are significantly larger in one set as compared to the other, you have to go for the dummy variable approach. So to deal with it, we add dummy variable. Okay. variable or variable, you can say. So let's start with a simple uh, model, okay, with one regression. And so let us consider a simple model with one regressor variable x and one dummy variable z. Remember, here we are using two sets of data. Just remember this. I have given you one of the example to understand what is the why we need to use the dummy variables. But here there are three sets of data I have used. But we are considering the case where now we have two sets of data, okay, A and B. Okay, but this dummy variable can take either 0 or 1. So these are the values which the dummy variables can take. Okay, so what the model will be there for? It will be y is equal to simple linear regression model beta naught plus beta 1 x plus, now you introduce a dummy variable alpha z plus epsilon. This is your new model now, including the dummy variables. So we set z is equal to 0 if it is coming from set A, and we use z is equal to 1 if the data are from set B. Okay, so based on this, what will be your fitted model? Fitted model, we have seen how to do a fitted model analysis. It will be y hat, which is equal to beta naught hat plus beta 1 hat x plus alpha hat z. That's all, right? So now if z is equal to 0 is for A, then for set A, what will be your fitted model? It will be y hat is equal to beta naught hat plus beta 1 hat x, because z is 0. So alpha hat z will be 0. But for set B, you have y hat is equal to beta naught hat plus beta 1 hat x plus alpha hat into z. And, but z is 1, so you can just write it alpha hat. Okay. Therefore, just look into these two sets, A set and B set. Okay. We will do one example, so it will be clear that time properly. So you have A set of data, B sets of data, and you have two this kind of straight line, because it's a straight line model. We are assuming a straight line model. Okay. So what is this alpha hat here? So this alpha hat, can we say that this is nothing but the difference? This is nothing but the difference between response level or response variables, you can say, between, or difference between response variables between the A and B. So for A, whatever the response variable is there, so variable of A and B. Okay, so you can see that for state A, the response variable is y hat, this one, beta naught hat plus beta 1 x. For response variable B, or set B, you have the response variable y hat, which is beta naught hat plus beta 1 x plus alpha hat. So if you subtract these two response variable, what you get is alpha hat, right? Because if you just do a subtraction here, beta naught cancels, beta 1 hat cancel. What you left behind is alpha 1, alpha hat. So that's why you can say that it is the difference between the response variable of A and B, right? Therefore, can we now again write this as y is equal to, instead of writing beta naught only, can I write beta naught x naught plus beta 1 x 1, you can say, it's okay. If you don't want to write, just put x plus alpha z plus epsilon. This is now my much more generalized model, where let us say that this is okay. This is suppose simple linear regression model. Okay, let us look at the multiple linear regression model. What will happen? Okay, this x naught is 1. It is always 1. Okay, so we are just introducing another dummy kind of a variable x naught, which is always 1. Because we have seen that in the earlier case, beta not only, right? So that's why we can write it. So what is this multiple linear regression model? This is x beta plus epsilon. And we know how to write the X matrix here. Here, there will be some difference. How it will be different? Let's see. So you have, in the first column, you have X naught, okay? Then you have X1, and there are so many regressor variables, the Xk minus 1. Here, K minus 1 regressor variables. And finally, you have a Z, okay? X naught, as I have already defined, is always 1. And we know that when we have used multiple linear regression model, we have always kept the first column as 1. Right? We have solved so many questions and we have kept it 1. That 1 is represented by x1. That's all. Okay. And there are so many values of different regressor variables that you can put. Finally, at the z, you have to put either 0 or 1, right? So z will be either 0. So for a, it will be 0. So up to some level it is 0 and then it is 1. That's it. Right? So all those things up to where it is 0 is here is coming from set A. And all from all the which are 1 in Z column are coming from set B. This is now your new X matrix. Okay. So Z is already covered here. But then what will be the beta then? Okay. So the fitted will be y hat is equal to x beta hat. This is now new x. What is your y? For y hat, or you can say the y matrix, you can say this will be nothing but the y1, y2. So many, whatever, exact same thing you can write. There is nothing changed. But what is beta hat is beta naught hat, beta 1 hat, so on up to beta k minus 1 hat, and finally alpha hat. This will be included because we are including z in the X matrix. So its corresponding alpha also has to be there. So this is all based on this particular equation. Okay. So that is, so you can write this multiple linear regression model in much better way, like beta naught x naught plus beta 1 x1 plus beta 2 x2 and so on up to beta k minus 1 xk minus 1, all register variables we have used. Finally, with alpha into z plus epsilon. This is your actual model. We have fitted it into this, where x we have written it like this, where we have included this x naught here and z. Earlier case in the multiple linear regression model, if you remember, x naught we don't write, right? We just keep it only beta naught, and we put the first column as 1. Here we are just writing that as x naught. That's all. Okay, so this is how the approach should be. Fine. And for multiple linear regression model, we know how to calculate beta hat is the same thing. So x prime, x inverse, x prime, y. This is how you calculate beta hat. We have seen that. And we will be doing today also. Okay. Only thing, the X matrix now is different. Is this. The X matrix is this. Right? So, yeah. So this is what it is. So what you can see here, when you have when you have two sets of data, when you have two sets of data, say A and B, you are using two dummy variables, and what are those two dummy variables? One is x naught, another is z. Okay, these are the two dummy variables which you are using, where x naught and z, if you look at, you are putting x naught always 1 and this as 0 or 1. This for A, this is for B. This is what you are using. But, well, if you are not using any dummy variable, suppose you have one set of data, then there is no question of dummy variable, right? When you have one set of data, say suppose A, so from one ocean only you are taking some data. You don't need to use any dummy variable, right? But still you are actually using this X naught. We don't say it, but we are actually using this X naught. Okay. So actually excluding X naught for two sets of data, you are actually using one dummy variable, that is Z. Actually. But we have introduced this X naught as another dummy variable. So there are two dummy variables. So just remember, whenever question comes and asks that, suppose you have two dummy variables, sorry, two sets of data. How many dummy variables you should use, excluding X naught? Okay, then you have to say one. That is Z. But if it does not mention, then you have to use X naught and Z. Just look at the question, what is there in the model. Okay, so that is what is for the two sets of data. Now let's see for the three sets of data what I have introduced: Indian Ocean, Arabian Sea, and Bay of Bengal. Okay, three sets of data. Then how will our analysis change? So let's look into that. Now for three sets of three sets of data. So let's see how many dummy variables we will have. So we will be using Z1 and Z2. Now we have in actual two dummy variables, but as you can see in the earlier case, we will introduce another X naught. So three sets of data, you actually will have three dummy variables. But remember, it is including X naught, including X naught. But excluding X naught, there are only two. This. Okay, so this how we will be using is that we'll be using 1 comma 0 for set A, okay, 0 comma 1 for set B, and 0 comma 0 for set C. See, you can interchange everything. You can write 0 0 for A, 0 1 for B, 1 0 for C, whatever you can do. Based on that, just remember your analysis when you are doing further analysis, which we will be doing, those things, those definitions will be changing. So be careful about it. So either you use this way, then whatever I will be writing, that analysis will remain the same. Otherwise, just its definition will change. That's the thing. So let's see what will be there for my, let's say, multiple linear regression model. Then what it will be? It will be beta naught x naught same way. So this is a dummy variable already introduced. Then beta 1 x1 plus beta 2 x2 plus so on up to beta k minus 1 xk minus 1, which we generally say, plus alpha 1 z1 plus alpha 2 z2 plus epsilon. This is now my three sets of data multiple linear regression model. You can use simple linear regression model where all these terms will be gone, zero. Okay, so this is generalized MLR, multiple linear regression model. Okay, then what will be your X? Your X matrix will be something like this. You first write x naught, then x1, so on up to xk minus 1. It will be always there. Then you have z1 and z2, right? So x naught will be always 1. It will be always 1, so it will not change. Now, changes will happen in z1 and z2. So it will be either 1 0, so on. Then somewhere it is 0 1, and so on. And finally it will be 0 0. Okay. So this is how the so this is how your so 1 0 corresponding to that is coming from set A, 0 1 is coming from set B, and finally 0 0 is coming from set C. Okay, so this is how the X matrix has to be formed. And then similar thing. But now what will be your beta hat matrix? It will consist of everything: beta naught hat, beta 1 hat, so on, beta k minus 1 hat, and then alpha 1 hat and alpha 2 hat. Okay, so these are now my new beta hat matrix for three sets of data. Okay, So based on that, now can we write what will be the equations of A set of data, B sets of data, and C sets of data? So let's see. For the A set of data, that is for in our example which I have given, let's say for Bengal, what will be the linear fit? It will be y hat, which is beta naught hat x naught plus beta hat x. I'm just writing beta hat x. It can be beta one plus beta two, so on, many things. Okay? Multiple linear regression plus alpha 1 hat. Why? Because it will be 1 0, right? So come here, z1 is 1, so alpha 1 will remain, z2 is 0, alpha 2 will go up. Okay, so this will be your A. For B, you have y hat is equal to beta naught hat x naught plus beta hat x plus alpha 2 hat because it is 0 1. So alpha 2 will remain because z2 is 1, but z1 is 0, so alpha 1 hat is gone. For the C set, both are 0, so you will be having the simple beta naught x naught plus beta hat coming from 0 0. One thing to note here is that in all the three cases, you have the whatever way we have used the dummy variable, like this equations, alpha 1 z1, alpha 2 z2, or in two sets of data, we have used alpha z. In all the cases, you can see that your fitted model has same slope and same intercept. Very interesting. See, each of them coming from different sets of data has the same slope. Means, okay, the intercept might be different because alpha 1 hat is being added, beta naught hat plus alpha 2 hat, and this is beta naught hat. Okay, so I'm taking my words back. Not same intercept, different intercept, but same slope. Look at this beta hat, beta hat, beta hat. Same slope. So in all these three cases, we have same slope. And we know from very basic concept that if you have three straight lines with same slope, that means they are parallel lines. Okay, so in all the cases, we can see that whenever you will fit a model, whether it is a two sets of data or three sets of data, your slope remains same, intercept will change. That means something happening like this. Okay, something happening like this. This is x, this is y. Say, let's say simple linear regression model. So in one case it is this, second case it is this, third case it is this. Something means your slope, sorry, intercepts are changing, but the slope remains same. Three parallel lines. Okay, so A, B, C, whatever we want to write. Okay, so this is what is happening. Fine, you will see that how it might be possible that the data which you have, it might not have same slope for A, B, and C. It might be different. So those things, those generalized things, we will be talking later. But right now, let us focus on this. Let us have the same slope. It does not matter, and but the intercepts are different. Let's see what we can analyze from these three lines. Okay, let's look at alpha 1 hat. What does that represent? Look at the alpha 1 hat. Okay. What is this representing? It is actually representing the difference between response variable or difference in response variable between set A and set C. Look at this. Isn't it true? See, in case of A, this thing is similar, and C, this thing is similar. Only difference is alpha 1 hat. Therefore, A and C, if you subtract A and C response variable y hats, then you will get alpha 1 hat. Similarly, alpha 2 hat is same difference in response between B and C. Correct? Just look at it. This is same. Only difference is alpha 2. And the last one is that now if you just subtract say set A and set B, then what do you get? Alpha 1 hat minus alpha 2 hat. So let's look at that also. Alpha 1 hat minus alpha 2 hat. This is nothing but difference in response between sets A and okay. Now we will be using the dummy variable. We have used dummy variables so far, but this alpha 1, alpha 2, and alpha 1 minus alpha 2, these has to be significantly larger than what? 0. Right? If these are 0, say alpha 1 hat is 0, alpha 2 hat is 0, nearly 0, then there is nothing important to use the dummy variable. You can see that for all the three lines, it is the same, right? So if alpha 1 hat, alpha 2 hat, they are not significantly different from 0, then there is no requirement of using dummy variable. You can see that all the lines will have the identical slope, identical intercept. There is no requirement, right? So we have to introduce dummy variable only when your alpha 1 hat, alpha 2 hat, or alpha 1 hat minus alpha 2 hat, this has to be significantly different from 0. And when you are trying to understand the statistical significance, what you have to do? You have to do the statistical significance tests for that. We will be doing that. Okay, so let me write whatever I have said. So we will find how significantly the alpha 1 hat, alpha 2 hat, and alpha 1 hat minus alpha 2 hat are different from 0, right? This is what we will be finding. Because if the difference is not significant, if it is not significantly different from 0, so I'm writing if difference is not significant, then we don't require we don't require to use any dummy variable. As we can see, because alpha 1 hat, alpha 2 hat, they are nearly 0. So there is no requirement. That means entire data, if you fit whatever the line you get, that is fine. There is nothing wrong in it. Okay. So this is any double variable. Okay. So this is what the thing. So for this, we need to do some tests. And we generally use t-tests for this. Okay. But after this, we will be using generalized concept where all possibilities will be used. There we will be using the express sum of squares technique, that is F test will be used, and we will see that, and you will see that mostly in the assignment questions and all, you will be not using these things like alpha 1 z1 plus alpha 2 z2. We will be using the generalized part. This is only to show that for two sets, three sets, how many dummy variables are using, and with a simple equations. Okay, so mostly you will not use this. You will be using whatever the generalized is going to be. Fine. Let's see what you have. So this is t test. So H naught will be that simple. Alpha 1 is equal to 0. H1 against the alternative hypothesis, that is alpha 1 is not equal to 0. Always remember this hypothesis testing. This is for the population parameter. It is not for the estimated parameters. Just remember this. So I cannot write alpha 1 hat. I have to write alpha 1 is equal to 0, alpha 1 not equal to 0. Okay. So based on that, our t statistic will be alpha 1 hat divided by the variance, right? So this will be root over x prime x inverse 3 3. Why I'm writing 3 3, I will explain. MS residual. MS residual, you know that it should be there because sigma square is unknown in most of the cases. And we know that MS residual is the best estimator for the variance. All right. So this is okay. Why 3 3? 3 3 because if you remember the beta hat, one is beta naught hat, next is beta hat, then alpha 1 hat, then alpha 2 hat. Okay. Because of which third element is your alpha 1 hat and you are testing for alpha 1. That's why the 3 3 element has to be used because this beta hat, its variance of beta hat will be a variance covariance matrix like this. You have diagonal elements So this has to be used because this is corresponding to the alpha 1 hat. Okay. So similarly, so if this T statistic modulus, because both way it is okay two-tailed. So it is T alpha by 2 and residual degree of freedom. If this is the condition, then H1 is accepted, and we will say that yes, alpha 1 is significant at some level, and hence we can use the dummy variable. Okay. Similarly, for alpha 2 hat, there will be some another hypothesis testing. Alpha 2 is equal to 0. H1 alpha 2 is not equal to 0. In this case, what will be the test statistic? Alpha 2 hat divided by root over x prime x inverse. Now what it will be? Alpha 2 hat is corresponding to the fourth element. So this has to be used. It will be 4 4 into MS. Okay. So that's all. So again, same condition, E is greater than E alpha by 2, the degree of freedom, whatever it will be. And based on that, you have to test the hypothesis. Fine. So, and finally, it will be for the alpha 1 minus alpha 2, which is alpha 1 minus alpha 2 is equal to 0. And each one will be alpha 1 minus alpha 2 not equal to 0. And for that, your statistic will be like this. This will be variance of alpha 1 hat minus alpha 2 hat. So how will you write? So we know that variance of alpha 1 hat minus alpha 2 hat will be nothing but variance of alpha 1 hat plus variance of alpha 2 hat minus 2 into covariance of alpha 1 hat alpha 2 hat. So how will you do that? So again, if you look at variance of beta hat, the matrix, which is a variance covariance matrix, here you have the diagonal elements 4, and this is the covariance of alpha 1 hat, alpha 2 hat. This is variance of alpha 1 hat. This is variance of alpha 2 hat. So this is this, and this is that's right. In this way, you can have your statistic. And in the same way, you have to use the test hypothesis. Based on this, you say that whether each one is accepted or each one is accepted. This is how the thing is. Okay. So now uh, it is being explained in the Turkey data problem. So uh, maybe you can refer to the lecture notes which are already provided in the NPTEL. So you can look into it that how it is being solved. Because for the Turkey data problem, I think it is being solved in the video lectures and notes. So I'm not going into the details. If time permits later, I can show. But right now, let us fix up to this and let us go for the generalized taking. That is all possibilities. So we generally take all the possibilities. Here, whatever I have shown so far for two sets of data or three sets of data, we have shown for the case where there are three parallel lines. Beta is same. Okay. But it can be possible for some data, beta might not be same. Okay. For that, what we can use. So now it's a generalized problem. Let's see the generalized case. Okay. For the generalized case, how we can do it? See, let us write first. So interaction terms involving dummy variable. So this is the generalized case. How the interaction term will come, I will tell you. Okay. So first is that we have suppose two sets of data. Okay. Say A and B. Okay. Two sets of data we have. Number two, we will be using some simple linear regression model. And the third is that there are four possibilities. So what are those? We will be talking about this. Okay, there are four possibilities. So let's see one by one. the first case is that two distinct lines, because there are two sets of data, so there will be two distinct lines possible. Okay, two distinct lines. Okay, so for the first set, suppose we have y is equal to beta naught plus beta 1 x. Okay, and for set B, we have y is equal to some gamma naught plus gamma 1 x. Okay, these are two distinct lines. Why? Because their slopes are different. Slopes are different, beta 1 and gamma 1, and their intercepts are also different, beta naught and gamma. Okay, so two different sets of data can be represented by two distinct straight lines because we are using simple linear regression model. Okay, so for linear regression analysis. So now, just suppose this is one of the lines, this is another line. Okay, this is suppose gamma naught plus gamma 1x. This is suppose beta naught plus beta 1x. This is corresponding to what? A set, and this is corresponding to B set. Okay. This can be one of the possibilities. For some data, it can happen like this. We will see that for which case what will happen. For that also, we will be testing something. Let's see the second case where you have two parallel lines. We have seen this case. Okay. In the earlier cases, whatever we have done, we have used two parallel lines where slopes are same. So what will be for the two parallel lines? For A set, you have y is equal to beta naught plus beta 1x. For B set, you have y is equal to gamma naught plus beta 1. Slopes are same, you can clearly see, but the intercepts are different. So how this will look like? Something like this. But beta naught plus beta 1x is like this. And you have gamma naught. How I have written? No. So gamma naught plus beta 1x like this. Okay. So this is gamma naught plus beta 1x. This is for set B. And this is beta naught plus beta 1x for set C. This is x, this is y. Okay, this kind of thing we have seen it, right? Let's go to the two sets case. See, look at it. For A set, we have got this. For B set, we have got this. See, beta 1 is same. In one case, it is beta naught hat as the intercept. In the second case, it is beta naught hat plus alpha. So this is the same thing. Okay. For the third case, you have now two lines with same intercept. Now slopes are different, but intercepts are same. This is another possibility, quite possible. So A is y is equal to beta naught plus beta 1 x, and B is equal to y is equal to beta naught plus gamma 1, right? So for that, you have a graph looking like this. Okay, so this is one, and another is the same intercept but with different slope. So this is beta naught plus gamma 1x. This is beta naught plus beta 1x. This is corresponding to A. This is corresponding to B. X, Y. Right? This is one of the possibilities. And the last one is that there is nothing different. All are identical, single fit, identical. So for identical, you have A same as B. Beta naught plus beta 1x means your slope intercept both are same. Y is equal to beta naught plus beta 1. In this case, actually you don't need any dummy variables, right? So same slope, both for A and B, right? So these are the four possibilities which you can have. Okay, so now we can take care. Now, how will we take care of all these four possibilities? So we can take care of all these four possibilities by choosing two dummy variables. Okay, you have two sets of data, so you will have two dummy variables, including x naught. So what we have written earlier, same thing we will be writing. This will be 1, 1, this will be 0, 1. Right? This is for set A, this is for set B. Same thing will be writing. But the equation will be much more generalized. Look at the equation. This is beta naught plus beta 1x into x naught. This is one of the dummy variables. And second is z times alpha naught plus alpha 1x. You can write it as gamma naught plus gamma 1x, which I have shown earlier. Okay. So this is what you have. Okay. This can be written as, means you can write this as gamma naught plus gamma 1x. What the earlier things we I have shown. But since it is written like this, I am not changing it. Fine. So this plus epsilon, of course. So what will happen is that we can further write this as beta naught plus beta 1x. If x naught is 1, so we are just writing this. Finally, z alpha naught plus alpha 1 x z plus epsilon. This is this interaction term which we were talking about. So in the generalized case, we have this interaction terms. Of course, it will be there. Okay. Now, for set A, therefore, the model becomes, that is for z is equal to 0, y will be beta naught plus beta 1 x, z is 0. Therefore, nothing. Correct? And for B, z is equal to 1. That is y is equal to beta naught plus beta 1 x plus alpha naught plus alpha 1 x plus epsilon. Correct? So this is what your models for A and B. Okay, in the earlier case, it was only alpha naught, but here, since the interaction term is present, we are also including this alpha 1x because it is possible that the slopes might also be different, which we have not considered earlier. All right, so these are the things. Now, we need to test certain things to show that really we need the dummy variables. Okay, so we need to test for each of these possibilities which we have discussed. Okay, so first let us see two parallel lines. Two parallel lines. So for parallel lines, let's look at the equation. Okay, let's look at this equation for time. If you need two parallel lines, what you will test for? See, for two parallel lines, slope should be same. For two parallel lines, slope should be same. Therefore, if I put alpha 1 is equal to 0, then only the slope will be same for both the cases. Look at this two. If alpha 1 is 0, slope will be same for both the cases. Right? So, let us test for, therefore, for two parallel lines, let us test for alpha 1 equals 0 against the alternative hypothesis, alpha 1 is not equal to 0. So, if H naught is rejected, if H naught is rejected, then we can't go for parallel lines. Okay? We can't go for parallel lines. That means slopes are really not same. Okay? So this is what the thing, but how will you do it? I will come to it later. But let us first see two lines with same intercept. Okay, two lines with same intercept. Okay, let's look at here again. Okay, two lines with same intercept. What we need to do here? See, slopes might be different. It does not matter, but intercept should be same. Let it be beta naught. Therefore, alpha naught has to be 0. then only beta naught will be same for both the cases. So put the null hypothesis as alpha naught equals 0. Against the alternative hypothesis, alpha naught not equal to 0. Again, if H naught gets rejected or H1 is accepted, both the cases, you can see that alpha naught is therefore not equal to 0. Alpha naught is really not equal to 0. Then we can't perform. We can't go for we can't go for same intercept lines. Okay. And next is the identical case. Identical. For this case, we have to use both alpha naught and alpha 1 has to be 0. Right? Because identical means what? This line and this line should be same. All others should be 0. So all coefficients you put it 0. H1 when H naught is not true. Okay. So again, so you can see that if H naught is rejected here, then you cannot go for identical case. So I'm not writing this. Let me show that how you will do this calculations. So you will use for testing, what you need is extra sum of square technique. Okay. So what it will be? F will be SS regression of the full model minus SS regression of restricted model divided by the degrees of freedom in the numerator divided by MS residue for the full model. So if this F, this is actually equal to F of alpha, level of significance, this is percent, and the degrees of freedom at the numerator divided by the degrees of freedom of the, or the residual degrees of freedom. So I will show you how to do this using a practice question. Okay, let's go for it. This will be clear and then we will go further. Okay, so let's go for one of the practice questions. So what is given? Let me write x, y. This is 8, 0, 12, 2, 9, 7, 8, 6. Right? And corresponding y is 5.3, 0.9, 7.1, 2.4, 5.1, 4.4, 5.2, and 3.8. All right. So this four data, first four, is coming from some set A, and this is coming from some set B. Okay. So look at it. That how many sets of data? There are two sets of data. We can clearly say. Therefore, there must be two dummy variables, including x naught. So actually, there is one dummy variable z. So you know how to do this. Z has to be 0 for the first set and 1 for the second set. So just put it here is equal to 0 for the first four and it is equal to 1 for the second set. So here, so we can write here we have two sets of data. So we have one Z and one X naught. X naught is understood on this own. Okay, so let's do one thing. Let us first fit all these together. Okay, for this we require x minus x bar, y minus y bar, and x minus x bar, y minus y bar. Simple linear regression. Remember. Okay, so I just quickly write all these values and just look into it right now. You can solve it further later. So just look into this 5.5 minus 4.5, 2.5, 0.5, 1.5, and minus 4. Let me write y bar also 1.025 minus 3.375. This is 2.825. This is minus 1.875, 0.825, 0.125, 0.925, and finally minus 0.475. This multiplication you can do 1.5 into 1.025 like that. Okay, so these are done. And how I calculated this x minus x bar? You should have x bar, so that is 6.5, and you should have y bar, which is 4.275. Okay, based on this, these are calculated. Okay, so what we are trying to do is that first, let us fit based on all the data. Okay, so for that, we will be using y is equal to beta naught plus beta 1 x plus epsilon. And the fit will be y hat beta naught hat plus beta 1 hat x. Okay, you know from simple linear regression model, beta 1 hat is nothing but, so it is summation. You know that this is x minus x bar into y minus y bar divided by summation x minus x bar whole square. So these are I. Okay, summation is also in I. So just what you have to do is that you have to sum all this and you have to sum square of this. So I have all the values. Let me just quickly write it and so that it will be clear. So you can check later on. So it will be 51.1985 divided by 104. This thing is 104. This is this. Finally, you get 0.4923. And what is beta naught hat is nothing but y bar minus beta 1 hat x bar. Just remember from the simple linear regression, y bar I have already written 275 minus 0.4923, sorry, 23 into 6.5. This gives you 1.075. So based on the two sets of data together, the actual fit, we get y hat as 1.075 plus 0.4923 into x bar. This is the actual fit including all data, right? Okay, fine. Let us do first this because this is required. When it is required, you will see. Okay. Now, actual question. The question is that, let me write the question based on the data given as x, y, and two sets. So, using one dummy variable z, distinguish two groups z is equal to 0 for set A. So, this is given in the question, so you don't need to initially fill the gap. Just read the question. It is given that what is the value of z for which set, and z is equal to 1 for set B, right? Now we can fit a model as given. So y is equal to beta naught plus beta 1x plus alpha naught z plus alpha 1 zx plus epsilon. So you can see that this is the generalized model which they have used. So you need to fit this, and the corresponding question is that calculate least square estimate of beta 1. This. okay, and alpha 1. So you know that alpha 1, beta 1. So ultimately you have to find out the beta hat. That's all. Okay. So what we will do here, the solution is that here you have to use the X matrix in a different way. How will you use it? Is this. So first column is the X naught dummy variable, which is excluded here. They have said one dummy variable. So for all the observation, 8 values are there. So n is equal to 8. Okay. So you write this, right? 8 values of 1. Next is the X values 8, 0, 12, 2, 9, 7, 8, 6. Next, so this is your X. Next is Z. Okay. So how will you write it? So what you will do what is that you write this 0. Okay. So what you have here is the alpha naught and alpha 1. So there are two things which are there, right? So for that, what you write is that uh, you make it Z and make it ZX. Okay, for the generalized case, you have to do like this. So Z is what? 0 for set A. So just put 0 here. This will be 1. All 1. Correct? Because these are coming from B set and these are coming from A set. So you can write like this. So Z into X will be similar. And 1 into 9 will be 9. 1 into 7 will be 7. This will be 8. This will be 6. All right. So you have to do like this. Zx can be considered as one variable. Z is another. This is now my new X matrix, which is 8 cross 4. Right? What is Y? Y is given all those data. So 5.3.9, 7.1, 2.4, 5.1, 4.4, 5.2, and 3.8. So it is 8 by 1. All right. So what you need to do is that beta hat can be calculated as x prime x inverse x prime y. So let me just quickly tell you what is the x prime x inverse. You can always do it using some coding or something. So just I so it's a big matrix. I don't know whether you will be able to write or not. So just writing the three places of decimal, you can include all minus 0.06, minus 0.582, and 0.06. Okay, so this is minus 0.06, minus 0.582, this is 0.06. So you can see that's kind of a symmetric matrix. 0, 1, 0, or 0, 1, 1 can you write? This is minus 106 again. This is minus 1, 0, 1, 1. This is 0.06. This is 0.121. And this is minus 1.56. This is 0.21. This is minus 1.56. And this is minus 0.011. Okay, so I'm not writing the full. You should write the full so that you get the accurate answer. Finally, x prime y. In the same way, the way we have calculated earlier for the multiple linear regression, same way. So this 34.2, 273.5, 18.5, and 141.1. All right. So once you have done this, just calculate beta hat based on the above formula. What you will get is 1.4175. This is 1.14175. Next 0.5060. Next minus 0.04175. And next minus 0.03604. All right. So this is what you have got. So you have got your beta naught hat. This is your beta 1 hat. This is your alpha 1 hat. And this is your alpha 2 hat. No, sorry, alpha naught hat. This is alpha 1. Okay. So this, you know, then alpha naught and everything you can calculate. Now, now comes the hypothesis testing question. Second part is consider the data to see whether, so using hypothesis test, you to see whether a single straight line means what? Identical. Single straight line model fit all data or no. So for that, what you will use? H naught, single fit. Let's go to the equation again. For the single fit, you need only this, correct? Alpha naught and alpha 1 should be 0. So you have to put your null hypothesis, alpha naught is equal to alpha 1 is equal to 0. And your alternative hypothesis will be H naught is not true. And as we have discussed, this has to be understood using extra sum of square. And what is the formula of that? SS regression of full model minus SS regression of restricted model. So this restricted model will be based on H naught divided by the degrees of freedom of the top numerator divided by NS residual of the full model. Let's calculate this. So this will be clear that how to do this kind of a test. Okay. So let's see what is a full model. Full model is this. That is y hat is equal to beta naught hat plus beta 1 hat x plus alpha naught hat z plus alpha 1 hat z. Right? And restricted model is when alpha naught and alpha 1 are 0. So it will be y hat, which is beta naught hat plus beta 1 hat x. Okay, so this is your restricted model. All right, so this is known. Now, look at how many parameters you have, unknown parameters. 1, 2. In the restricted model, you have two unknown parameters. Unknown parameters. Okay, but in the full model, how many parameters? 1, 2, 3, 4. 4 parameters. Then in the top, when you are subtracting it, how much will be the degrees of freedom? 4 minus 2. That is 2. All right. So F will be therefore, let us on the right, SS regression of the full model minus SS regression for the restricted model divided by 2 degrees of freedom divided by SS residual of the full model divided by how much will be the degrees of freedom for the SS residual. That is, we can calculate because if suppose n is the number of observation minus how many unknown parameters in the model? 4. So it will be n minus 4. All right. So this is the way you have to do it. So here n is 8. So this is nothing but 8 minus 4, which is 4, because number of observation is 8. All right. So this is how degrees of freedom can be calculated when you have this kind of a test, and you just need to calculate now this is regression and all. Okay. Let's look at for the full model SS regression. Okay. So SS regression, there is a formula in multiple linear regression model. Just if you remember, it's best. This is how you can calculate the SS regression. All values are known. So you have this is nothing but you can calculate 171.5928 minus number of observation is 8. Y bar square 18.275. Y bar is known, so Y bar square can be calculated. This will give you 25.3878 for the full model. What about SS residual for the full model? Again, there is a formulation y prime y minus beta hat prime x prime y. This gives you 0.3272 for the full model. But then what is MS residual? Because we need this for the full model. So it will be SS residual for the full model divided by 8 minus 4. So this gives you 0.0818. Fine. So we have calculated for the full model. Now, what is the restricted model? Is this beta naught plus beta 1x. And we have already made it fit earlier before the question starts. This. So from here, can we calculate uh, the SS regression? Yes. How to do that? We know now this SS total is nothing but what? Summation yi minus y bar square, which is nothing but 25.715. How will you get it? This from here. Look at the table. We have already calculated this. Square these values and add it. So that will give you SS total, right? Fine. How to calculate SS residual? This is for all for the restricted model. That is beta naught plus beta 1x. So SS residual is SYY minus beta 1 hat square SXX. SYY is nothing but SS total. So it is 25.715. Beta 1 hat we have already found out. Beta 1 hat square will be 0.2423 into SXX is 104. We have seen this. This gives you 0.51. Okay. This is SS residual. But SS regression we know is SS total minus SS residual. Correct? So this gives you uh, answer to be 25.205. This is for the restricted model. Now you can calculate F, which is 25.3878 coming from what? Coming from this SS regression of the full model minus SS regression of the restricted model divided by 2 degrees of freedom. We have seen this. Okay. And MS residual finally for the full model. Once you do it, it will come out to be 1.1173. Now, if you look at F2 degrees of freedom, 4 degrees of freedom for this, and say zero point 0.01 level, it is 18. If you look at F2 for 0.05, it is 6.94. So in all the significance levels, you can clearly see that F, which we have calculated, is much less than these F24.01 or zero point 0.05 level. Therefore, we can conclude that H naught is accepted. That means what? Alpha naught is equal to alpha 1 is equal to 0. That means we actually don't need any dummy variable. So, what does this indicate? That single line fit is possible. If H naught is accepted, then only single line fit is possible. Otherwise, not is possible. Okay. So, just you can write whatever we have got from uh, using this beta hat. If you look at that, so y hat is 1.1417 plus 0.506 x minus something z, zx. All this will be 0 in this case. So this will be the line. And what we actually got for all the data, for all data, we got earlier this 1.075 plus 0.4923x. You can clearly see that these are nearly similar. Okay, so whether you go ahead with this dummy variable approach, this will also give a similar result to that of this. Okay, so this is a question which shows you how to test the hypothesis and how to solve it. Okay, using the extra sum of squares. So this is what I wanted to show. All right, so you can now do this based on this. So if assignment questions comes like this, okay. Now, so I just wanted to show it for 3 sets of data. Okay, 15 minutes left, so we can quickly write it. Now that you have understood the extra sum of square technique, it will be easier for you. Okay, so let's quickly go ahead. For the three sets of data, practice question is over. So let's go for now three sets of data. Generalize quickly. Just quickly I write so that it is easier for you to solve the questions. Okay. So for three sets of data, there must be three dummy variables. I just write quickly. You can understand everything. So y is equal to x naught beta naught plus beta 1 x plus z1 gamma naught plus gamma 1 x plus z2 delta naught plus delta 1 x plus etc. Right? Two dummy variables plus one. So three dummy variables. X naught is one already. Okay. So you can write it further. This will be beta naught because x naught is one. So I'm not writing this plus z1 gamma naught plus z1 gamma 1 x interaction term plus z2 delta naught another interaction term plus etc. This is the model. And you can write, if you have a multiple linear regression model, this is simple linear. So you can write like this. First is x naught, the x matrix. We have seen it in the practice question. All one, right? X1, x2, up to xk minus 1, whatever you wanted to write. Then comes z1, then z1x, z2, and z2x. This has to be the X matrix. Okay. So Z1 or there are three sets. So how will you write this? So Z1, Z2. For A set, it is 1, 0. For B set, for three variables. Okay. For three sets of data, it is 0, 1. And for C set, it is 0, 0. So correspondingly, you write this is 1, this is 0, so on, 0, 1, so on, and left 0, 0. Okay. Corresponding to Z1x and Z2x will be calculated. All right. So now the testing. So testing is that there are three testing possible. We have seen that in the two variables or two sets of data. So for the testing, you have number one, identical. Means three lines are identical. Three lines identical. For that, what you have to do? Identical three lines means what? Okay. This should be same for all the cases. So gamma naught, gamma 1, delta 1, all should be 0. So your hypothesis will be gamma naught is equal to gamma 1 is equal to delta naught is equal to delta 1 will be equal to 0. And what is the alternative? H naught is not true. Okay. So quickly if I write the F statistic, it will be SS regression for the full model minus SS regression for the restricted model based on this divided by how many degrees of freedom. See, in the restricted model, there are four unknown parameters. Sorry, in the restricted model, there are two unknown parameters because these are all zero. And for all models, you have one, two, three, four, five, six, six unknown parameters. So it will be 6 minus 2, right? Divided by MS residual full model, which will have degrees of freedom. How many? N minus 6. N is the number of observations. Okay. So based on this, you test the hypothesis and get. Okay. Secondly, so F greater than F4, 6 alpha. Alpha is the level of significance. If this is true, then H1 is accepted. H1 is accepted means what? We cannot go for identical lines because H1 is H0 is not true. Okay. Next is three lines parallel. So in this case, then what will be happening in three lines parallel? Slope must be same. All other things will go. So it will be gamma 1 is equal to delta 1 is equal to 0 and H naught is not true in the H1. Okay. So in the restricted model, you don't have these two parameters. Okay, so all other four parameters will be there. So it will be f is equal to SS regression of full model minus SS regression of restricted model divided by total full model. There are 6 degrees of freedom, 6 unknown parameters, and in the restricted model, there are 4 degrees of freedom because only gamma 1 and delta 1 are not there. Divided by NS residual for the full model, which has degrees of freedom n minus 6. Again, same. So this will be f2 comma 6 comma alpha, the level of significance. Fine. The last one. Now the three lines have same intercept. For same intercept, what you will write? H naught as gamma naught is equal to delta naught is equal to 0. H1 is H naught is naught. Right? So again, if you have to write, this will be same. Regression of full, this is regression of restricted divided by again 6 minus 4 because 2 are not here and n is residual for the full. That is n minus 6. So it will be f again 2, 6 and alpha. Alright, so this is how it has to be done. Fine. So just I quickly tell you why I'm writing this same intercept. Look at this model. Same intercept means for all the cases beta naught will remain, gamma naught and delta naught will not remain. Then only it will be same intercept, beta naught. Okay, so gamma naught and delta naught has to be put to 0 in the H naught. Right? So that's why this hypothesis is created. Fine. Now last 5 minutes I just right because I can see some questions in the assignments where you have two sets of data of quadratic or some cubic model. So I just quickly tell you about the quadratic model. You can always go ahead with further power models. Okay. So quadratic model y is equal to beta naught plus beta 1 x plus beta 2 x square plus epsilon. This is a polynomial regression, okay, of order 2. Whatever we have done so far is a polynomial regression of order 1. This is for order 2. Fine. So y is equal to x naught beta naught plus beta 1 x plus beta 2 x square plus because two sets of data. So two dummy variables, one is x naught, one is z. Alpha naught plus alpha 1 x plus alpha 2 x. Okay, so this is what you have. So beta naught here is intercept, beta 1 is slope, and beta 2 is actually called the curvature. Okay, this is what the dummy one. And of course, x naught and z if you write, for set A it will be 1 0, this will be 1 1. So z is actually 0. Now I just tell you how to go ahead with to test the possibilities quickly. Some of the things. For example, if you have to do test for identical model in this case, then what will you do? So you have this equation, right? This is your equation. Identical model means beta naught, beta 1, beta 2 for all the cases. Therefore, alpha naught, alpha 1, and alpha 2 all will be 0 as your null hypothesis. Alpha naught is equal to alpha 1 is equal to alpha 2 equals 0. And H1 when H naught is not. And you now know how to do this using extra sum of squares. So you can easily calculate the degrees of freedom and do so. Okay. Second case is test for same curvature. Okay. So test for same curvature. What is curvature? Beta 2. Beta 2 will remain same. Therefore, what to neglect is alpha 2. Alpha 2 should be 0. Then only beta 2 will be 0. So H naught will be alpha 2 is equal to 0. H1 will be alpha 2 not equal to 0. You can use F statistic. Okay, not a big issue. Fine. Third is let us say test for Same straight line. Okay, same straight line. Although it's a polynomial regression, but I'm saying that okay, the two sets will have same straight line. Straight line part is these two, beta naught plus beta 1. So this will remain same. Beta 2, alpha 2 will remain. Alpha naught and alpha 1 has to be 0. Correct? So for H naught, you have to put alpha 1 is equal to alpha naught is equal to 0. Okay. Also, you have to say that same straight line is oh, okay, fine, fine. Beta naught and beta 1, right? This creates a straight line. So this curvature term has to be 0. Alpha naught, alpha 1, and alpha 2 all has to be 0. So it's not only this. Alpha 2 also has to be 0. Beta 2 also has to be 0. And H1, well, H naught is not. Okay. So why is it happening? I'm just again explaining. See, in this model, straight line, same straight line will be represented by this only. Curvature will not be there, and all other terms here will be 0, right? Because we need this. Okay. So for that, all coefficients has to be 0 in the null hypothesis. And at last, so I will stop here. So test for same slope. Okay. For same slope. So how will you do it? Slope means beta 1. This one. This will remain. Okay. Same slope. Intercept will be there. Beta 2 will be there. So alpha 1 has to be 0 because alpha 1 is another slope. So that has to be 0. So put alpha 1 is equal to 0. Each one is easy. That is alpha 1 not equal. So in this way, you can create your own hypothesis and test it. So you will find most of the questions in assignment 10 is based on this kind of a thing. So you will be given an equation like this. You have to understand that what is said based on this, whether it is an identical model or same slope, same straight line. Based on that, you have to create a null hypothesis and test it. Okay. So one of these is this. These kind of questions may come. Okay. So it's based on all these whatever we have seen today. Okay. Now, if any question is there, you can ask. Otherwise, I can stop here. So any questions? It's a big concept. Okay, fine. Good. It's a large concept. Just revise this, whatever I will share today. You will be, I think it will be easier for you to solve the assignment questions because based on that only the assignment questions will be mostly based. So, so I have looked at the assignment. So based on that only those concepts I have highlighted. So you can do it. Okay. So with this, I think we should end today's session. Thank you.